Okay, so now we're going to go to section 4 again, still review just a little more detail with the exponential stuff that we mentioned before in whatever it was, section 2, I think. So again, exponential function is of the form a to the x. The reason it's exponential is because the variable is in the exponent, okay? Again, the domain is, that's the symbol for all reals. You could also write it as that, perfectly okay. The range, right, we can't get 0 or below. And it does depend on A. Again, there were two different looks. The first is if A is bigger than 1. The other is if A is between 0 and 1. Notice that I haven't included 1. Why? Well, because 1 to the x really is an exponential. It's a straight line. So we're going to omit that one. So as long as A is greater than 1, we have an increasing function here from left to right. Right? And when a is between 0 and 1, we have a decreasing function from left to right. Might be a good idea to recall these guys, right? The rules of exponents. Again, exponents really just shorthand for multiplication. So if you have x copies of a and y copies of a multiplied, we have a total of x plus y, right? Certainly the same for the division. X to the y we multiply, and then if we have ab, if there are x copies of ab, that means there are x copies of a and x copies of b. So again, this should be review. This is kind of related to what we talked about before, right? This is kind of, or should look like, y equal 2 to the x. What is y equal 2 to the x? Where it's a standard exponential where it's increasing from left to right. So notice that we have a minus sign here, so we're going to have to reflect it about the x-axis because plus y becomes minus y. And then we have a plus 3 in front, so we're also going to have to shift it up 3 units. So that's what it would look like. Okay, this is after the reflection and the shift. Notice that y equal 2 to the x is asymptotic to the x-axis, right? And after we rearrange this sketch, this has a new asymptote, which is up around 3. Okay. Also is no longer increasing, it's actually decreasing. So exponential models are very, very good for radioactive decay and also population growth. Now, the population growth we'll talk about in a lot more detail later on because your standard y equal a to the x does not do a good job because that actually continues to increase, which obviously populations do not do. But that's a discussion for later. Let's do a decay problem because that's a little easier and you don't have to mess with it as much. It's actually more realistic than the decay version. So here we have a half-life of strontium-90, everybody's favorite element. What does half-life mean again? Well, it just means that 25 years is the amount of time it would take for half of however much you start with here to decay into something else, okay? So if we have a 24 milligram sample, let's see if we can figure out a formula for what the mass is after a given number of years. So our initial start at time 0 is, we have 24, right? If we know the half-life is 25 years, then obviously after 25 years, we're going to be left with half of 24, which is what we have here. Okay. After another 25 years, we're going to be left with half of that. Now, instead of just writing 12 and then 6, I'm going to kind of leave the halves in there to see the pattern. So it's half of 24, which is the same as 1 over 2 squared, right? That's when m, that's the mass after 50 years. After another 25 years, it goes half again, so it's 1 over 2 cubed times 24. And, you can see the pattern here, what's going on. Well, it looks like whatever I put in here, right, that number there is that time over the half-life 25. So in general, we get that. And then, of course, using the rules of exponents, if you want to bring it back upstairs, you just negate it. You don't have to. The other one's perfectly fine, but whatever. Now, once I have an expression for the mass at any given time, I can now find the mass for any time, and I can also find how long to get to a certain mass. So if you want to find the mass after 40 years, well, you simply put in 40 into our expression and calculate that. It's around 7.9. Okay. Now, again, what can we have here as our base for exponential functions? Well, remember we said a has to be a positive constant. Now, of all the positive constants we have, there's quite a few of them, there's one that we really, really like for calculus, that is base e, okay? In other words, y is equal e to the x. What is e? Well, It's around, right, 2.71828, blah, 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 whatever. It's an irrational number, meaning the decimal representation never repeats and never ends. Well, it seems sort of an odd choice, right? Why not something nice like 5 or 2 or 10? And again, the reason is, I don't want to spoil it for you too soon. We'll see later. It's specifically for calculus. There's something that is unique about base E that's very nice, and we like it. It's more than between 2 and 3 here, so it's still from left to right will be an increasing function as we have here. That's what it looks like. How can we do this sketch again, given that we start with this? Again, you just do the order of operations. So it's minus x first, so plus x minus x, we reflect around the y-axis. Then we have a 1/2 in front, so that's a compression. And then we have a -1, so that's a shift down, right? So that's what we have here, right? So first we reflect, then we compress vertically by a factor of 2, and then we shift down 1 unit. And so again, we get something that looks like this. Okay, so we have a new asymptote because of the shift down. It's down at -1 now. We'll be dealing with exponentials, and you'll see in a few minutes logs as well, a lot. Okay, that's part of the STEM calculus. So here again is our worksheet, pretty straightforward, and as always, I'll post the key for this and send it out on Remind. And then we have the homework here for section 4, and that finishes that up.